Right.
You can start.
Okay,
Sorry, what were we asking?
yeah, about recording.
Okay, so welcome to another edition of the Gemini North Talk Series, being hosted at yet another physical location. So we are in the IFA Hilo building, and thank you very much to IFA Hilo for accommodating us. And to all the observatories along Observatory Row here, and all the institutions for helping us out, helping Geminites and C3VOites out this week as we deal with our IT infrastructure attack. So it is a pleasure for me to introduce Ekta Shah for people that don't know her. Ekta is a postdoc working in our group at UC Davis on the charting cluster construction with Woods and RL survey. Ekta got her bachelor's in University of Baroda, is that right, in India?
Yeah.
And then went to the Indian Institute of Technology for her master's in Bombay, before going to Rochester Institute of Technology, working with Jehan Kartaltepe of Cosmos Web fame on Galaxy AGN connections. So Ekta is going to talk to us about her PhD work and then some of the work that she's done with us as a postdoc. So the floor is yours.
Thank you, Brian, for the introduction and for the opportunity to work on this wonderful stuff. So as Brian mentioned, I will kind of start with the work I've done with my advisor for my PhD, and then I will transit to my current work. But it's all kind of related and it's all about our universe. So let's get started. Okay, so as we know, and many of us might have already seen these pretty pictures. So when we observe our universe, a lot of times we see kind of this kind of galaxy systems where it's, clearly two or even sometimes more galaxies, as you can see in the bottom right. They're kind of clearly interacting with each other, and you can see even just from this quick visual inspection, they are affecting like the morphology or the shape of the galaxies, right? You can see, I think I should write this because can you see my cards? Oh yeah. So you can see this kind of like tidal tails, and then also a lot of bright stuff happening throughout the galaxies. So it seems like galaxies as they evolve, many times they also come near each other and affect each other gravitationally. And this can have strong impact on galaxy properties. But how do we study them? Because as we know, this kind of galaxy interactions or even overall galactic processes, they happen on the time scale of millions to billions of years. And, we don't live that long, and apart from other things, like we cannot just observe same galaxies for millions of years. So barring those practical concerns, but so how do we study these processes, right? So one thing we can do, at least observationally, is we can observe populations of galaxies that are at different stages of interaction. So here you can see, you have some galaxies that are like somewhat far apart, then you have some population that is somewhat closer, and then finally you have things that are like almost about to merge, and then finally you have mergers. So it's very similar, somewhat similar to like if some alien comes here right now, and he's like, how does human evolve? And he might not see a single human growing, but then he might see Alice, and he might see Brian, and he might see people in between. So they might be able to figure out that you have like you have the populations that span a large range of some properties. So in this case, it's like the projected separation. And then if you do statistical analysis of that, of the range of the population, then you might be able to figure out that how this process might be happening in a real time, right? So how this kind of interaction might be happening in a real time, and then how it might affect galaxy properties. But then if you want to study the actual impact of interaction, what we should do is to compare the properties of these interacting galaxies with isolated galaxies, because we know that even by themselves, galaxies change, right? They're over the time they grow, their star formation change. So if we just observe galaxies, even interacting galaxies by themselves, and we see them having high star formation rate, that could be due to interaction, or that could be due to other properties like that. Those galaxies might be just larger or something, right? So if we want to specifically understand the impact of interaction itself, then the way to go is to compare the properties of these galaxies with isolated galaxies that have somewhat similar mass and other properties, so that the only difference between the two population is one is sample of interacting galaxies and other one is isolated galaxies. So whatever difference we see in their properties is mainly due to interaction, because that is the main difference between the two population. So that's what's been done in many observational studies in the local universe. So here we have an example of that. And as you can see, so the x-axis is projected separation. So for example, in this kind of sample, you can, once you have the information about the redshift of the galaxies, you can measure the projected separation of the two galaxies. So again, the idea is somewhat similar, like, you divide your population in samples of galaxies that are somewhat far apart to going, closer and closer. So things that have like larger separation over the right-hand side are things that are like somewhat far apart, and then eventually you consider populations that are much closer and closer, which means that closer the population, or more you go towards this direction, higher the interaction and higher the impact of interaction on galaxy properties, as we can see here. So in this case, they basically compared the AGN activity of interacting galaxies with isolated galaxies, and then took the ratio of the AGN property. So as you can see, stronger the interaction, stronger the impact of interaction on AGN activity, which means that these interactions do have strong impact on the AGN activity of galaxies. And similar trend has been also seen in star formation rate, where again, like closer the galaxies, stronger the interaction and stronger the impact of interaction on the star formation rates. Now, this is very important though. Both of these studies are based on local universe. And so this is based on observations, and similar thing has been also similar results has been also seen in cosmological simulations. So here we again see like, again similar trend of closer you go, so closer the galaxies are, stronger the interaction and stronger the impact on the, in this case, specific star formation rate of galaxies. But the same trend has been seen in the star formation rate and AGN activity of galaxies. So let's kind of summarize what we know. So again, all of the studies that I've shown so far are based on local universe. And so for that, observations as well as cosmological simulations and binary simulations, where you just take two galaxies and then merge them together, all of them show somewhat strong impact of these interactions and galaxy mergers on the star formation rate and AGN activity of galaxies. But we know that in the past, galaxies were very different, right? So for example, here we have star formation rate density of galaxies, the cosmic history of the star formation rate of galaxies. And as we know that actually right now, the star formation rate isn't much high. So if we go more and further in the past, so for example, on redshift of 2, that's when like a lot of most of the star formation rate and AGN activity of the universe was happening. And another thing we also know is as we go in the past, so for example, if we consider galaxies here, which is in the current universe versus galaxies around redshift of 2, they look very, very different. So on the left, we have a simulated galaxy in the local universe versus on the right, we have simulated galaxy in the high redshift universe, so around redshift of 2. Now, one of the main difference between them is the gas fraction. So the gas fraction in the local universe roughly is around 10%. And then around redshift 2 is around 60%. So as you can see, this is just isolated galaxies by itself, but even they look very, very different, right? You have a lot of clumps of star formation going on here. The gas density profile look very different. And another thing is like at this high redshift, galaxies were still forming. So the disk isn't formed yet. So the overall gas is kind of very hot and very turbulent. So this is very important to keep in mind when you study galaxy interactions and mergers. So this particular study, they looked at the binary simulation of galaxy interactions in low redshift universe and high redshift universe, where the main difference between the two is the gas fraction. So the galaxies that I just showed before. So if you take those galaxies and if you merge them together in simulations, now as you can see in the low redshift case, in left case, you have this very strong inflows that kind of feed the central AGN, and then you also have a lot of star formation, kind of increment of star formation because the gas kind of cools down. But as you go at high redshift, even right now, you don't see strong inflows towards the central region. And furthermore, as I mentioned before, the gas is kind of very hot at high redshift, so it's kind of difficult for it to cool down. And another main thing is also that, as I showed in plot before, that average star formation and AGN activity of galaxies is already very high in this high redshift universe. So it's kind of difficult to increase star formation and AGN activity even further. Versus like in local universe, the average star formation and AGN activity is not that high. So when you have interaction and merger, and if the gas is available, then you can have the strong inflows that can fuel AGN, that can result into triggering of AGN due to these interactions and mergers. So based on binary simulation, it looks like the impact of interaction and merger could be very different when you go to like high redshift and low redshift. But some of the binary simulations also show strong impact because overall gas fraction is very high in the high redshift universe. So you just have more gas available. So maybe in certain situations, there could be strong impact and you might result into somewhat higher star formation and AGN activity due to interactions at high redshift. Okay, so this is again what we know so far. So we already went through what we know based on local universe, which is, all the studies show, especially if you have like gas-rich interactions and mergers, then you have very strong impact of interactions and mergers on the star formation and AGN activity of galaxies. But if we go to high redshift, now high here is a little bit old-fashioned, so like redshift up to redshift of 2 or 3. So we are not talking about like JWST era yet. But when you go to like, when you move away from local universe to redshift of even 1, 2, 3, then then we don't know exactly what happens, right? So some of the binary simulations show that you can have like, weak to even strong impact. We don't know what do exactly the observations show, and we also don't know, like if we take statistical sample based on cosmological simulations, what do they show? Because binary simulations are based on only particular values of, stellar mass ratios and gas fraction and all. So when you take a larger sample, that's kind of more representative of what's happening in the actual universe or over a large scale. So this was the main motivation of my PhD work, is to study exactly how the star formation rate and AGN activity of galaxies get impacted around redshift of this important epoch of 0.5 to 3, and both based on observations and simulations. So, I was a bit ambitious, and because both observations and simulations have their own pros and cons. So I wanted to do studies using both and then see what kind of insights we can get. So, and as I mentioned, one of the main reason we focused on this redshift is also because it covers the, it's a very important epoch of galaxy evolution where a lot of stellar mass assembly is happening and a lot of star formation rate and AGN activity is happening. So with that motivation, let's get to actual study. So first part is using observations. So from now onwards, at least for the part of my PhD work, if you see this symbol of Hubble telescope, it's based on observations. And if you see this computer, very geniusly, that's based on simulations. So So for the observation study, now, as I mentioned that I am really interested in this, relatively high redshift stuff. So we need really deep data, deep multivalent data and spectroscopic observations. Why do we need spectroscopic observations? Is because, if you look in the sky and you can see like, oh, these two galaxies are together, but that could be just in the projected space, right? Unless you know their redshift, you don't exactly know like whether or not they are interacting. You can, so some of the examples that I showed that are based on visual identification, when you clearly have like two galaxies and you see these tidal tails. If you choose that, then maybe you can identify samples. But right now I'm focusing on galaxy pairs. So these are spectroscopic galaxy pairs that may or may not show this kind of like tidal tails and stuff, because those kind of morphological features, first of all, they are very hard to see at high redshift. And secondly, those kind of morphological features may depend on like what kind of interaction you have, whether or not you have sufficient gas, whether or not you are at particular angle to see them. So it's a very different kind of sample, and we want to be very inclusive. So we are also including like kinematic pairs that may or may not show this signs of morphological disturbance. So as I mentioned, first of all, like we need a lot of spectroscopic data, and then we are also interested in very massive galaxies and that are going through major interactions. So for that, we also need photometric observations and their mass estimates and all. So that this is why I use multivalent data from the CANDLES and Cosmos surveys. And I'm going to speed up a little. So I use the data from CANDLES and Cosmos survey, and apart from that, we also got a lot of our own DMOS data to identify these galaxy pairs. So I analyzed a lot of DMOS data, and then I selected best specs from all the surveys to then identify my galaxy pairs. So here are the main criteria that I used. So as I mentioned, the main redshift range for my study is from 0.5 to 3. And I'm interested in massive galaxies. So the stellar mass of the galaxies has to be more than 10 to the 10. And then I'm interested in major interactions. So the mass ratio of two galaxies have to be between 1 and 4. So these are like galaxies that are somewhat similar massive. And then we are interested in how they can impact each other. And then the projected separation between the two galaxies has to be less than 150 kiloparsec. And then ideally, we would like to restrict the 3-dimensional separation, but we cannot do that. So to restrict the third dimension in some ways, we apply the line of sight relative velocity cut of 1,000 kilometers per second. And applying this criteria, we identified about 1,345 galaxy pairs. So this is one of the largest known sample of spectroscopic galaxy pairs at this redshift. And so now that we have our spectroscopic galaxy pairs, as I mentioned initially, if we want to study the impact of galaxy interactions, what we really also need is a control sample, because the properties of galaxies can also get affected by like stellar mass and redshift and environment. So we really want to control for those things so that we can actually see the impact of just interaction itself. So that's why the next step is to generate a control sample. And for that, as I mentioned, like I select for each paired galaxy, I select 3 control galaxies, which are basically isolated galaxies that have somewhat similar mass, redshift, and environment to the paired galaxy. Furthermore, I also require the control galaxy to also have the spectroscopic redshifts, because there are different biases associated with spectroscopic observations. So we also wanted to control for that. And on top of that, I also select controls from the same field as my paired galaxy. So we really try to control for all these different biases and other properties so that we can actually see the impact of interaction. And here is again the distribution of my pairs and controls, and as you can see, they really match very well. So basically we are controlling for most of the properties that can affect the star formation rate and aging activity. And then now that for the pairs and controls, these properties are similar. So now if we see a difference in the star formation and aging activity, that's most likely due to galaxy interaction because that's the main difference between the two samples. And so with that, let's look at how the star formation rate compares between the two samples. And for that, basically, I estimate star formation rate using SET fitting, and I kind of find average star formation rate of the pair sample and average star formation rate of the control sample, and then take the ratio of the two. So the blue points here are the results of my study, and the black points are basically based on local universe, and these 3 points are identified based on visually identified samples of interactions and mergers. So as you can see, we see maybe like a slight enhancement of about factor of 1.2 in the closest pair separation, and then factor of about like 1.8 in our merger sample. But for the overall sample, we don't see much enhancement in our pair samples, especially when you compare to local universe, where you see like clear trend of increasing star formation rate enhancement with decreasing separations. Maybe in the smallest separation we see them, but for the overall large sample, we don't see much. So again, this is similar to what binary simulation suggested, where if you go from redshift like 0 to somewhat higher redshift, the level of enhancement that you see in the interacting pairs is actually lower at high redshift compared to the low redshift. Now let's look at AGN activity. So I identify AGN based on X-ray and infrared observations, and then I take the AGN fraction in pair sample and control sample and take the ratio of the two to define AGN enhancement. So here is our result, and along with the comparison with the local results. So again, the blue points are based on our study from X-ray observations, and these pink points are based on IR AGN. And again, as you can see, we actually don't see any enhancements in the pair sample. There is maybe like slight enhancement of 1.8, but the error bars are still very large to say exactly how prominent it is. So again, if you go from like low redshift to high redshift, we don't see was any enhancement in the AGN activity of galaxies. So this is again very similar to what the binary simulations have found. And
I have a question actually.
Yeah.
So are you able to derive any kinematic information from the DEMOS observations, in that you could potentially plot like normalize for V over sigma and look and see if galaxies that have a higher V over sigma ratio might show a more coherent increase versus galaxies that have a lower V over sigma? Because I guess that sigma is kind of a modulating parameter, right? The turbulence of the gas is kind of a modulating parameter.
yeah,
And so enhancements like tidal torquing may not, as you showed, may not be as effective when sigma is very high.
yeah, we haven't tried that. We have not tried that. That's a good point. Yeah, I'm trying to think like what would be the typical distribution. First of all, we will run into small number of samples, but then, yeah, I think one thing is like, if you look at maybe mergers or like late stage interactions, so this, maybe these points, and then maybe based on like visual information, you can, get some idea. But yeah, no, we haven't tried that. That's a good.
But I mean, so when you're already at the merging stage,
Yeah.
the kinematics are going to be largely dictated
Yeah.
by the.
I meant like, so for example, here, right, when you see like maybe two galaxies that are just about to merge, and yeah, maybe based on visual morphological features.
But even at further separations, it might be interesting to break it up into two subsets.
Yeah.
One where it's turbulence dominated, one where it's coherent velocity dominated, and see if you see any differences there.
It's a good
We should
point.
talk.
Yeah.
I have a question.
Yeah,
Please, sir. So for this plot, I guess, you said your mass criteria was that it needs to be above 10 to the 10.
Yeah.
But I'm guessing as you go towards lower redshift, the galaxies get more massive. And do you know what part of this SFR enhancement comes from those lower redshift galaxies being more massive?
So that's a good point. I did divide them by mass and redshift, and there was maybe like slight difference, but didn't see much. Yeah.
And so, yeah, I was wondering whether you tried with reducing the distance along the line of sight to define a pair, and maybe
Yeah.
if this could increase the signal, or what you.
Yeah, so I, in my paper, I did have, so the short RF studies, even in that case, we didn't see. So instead of using like 1,000 kilometer per second, I selected 500 kilometer per second. I actually started with 5,000 and then reduced it to 1,000 and then 500. But even in those cases, we didn't see much. I mean, maybe like if you go like 100 or something, you might see, but then how many galaxies you have? And that's the thing, like even for this low redshift studies, it was like 500 or even 1,000. So in theory, you should still see something if it was there. So, yeah. Okay. So we were at the simulations. I think. Okay, I think I have summarized them enough. So as I mentioned, like we don't see much enhancement in the pair sample. We see maybe slight enhancement in the merger sample for star formation rate, and then when it comes to AGN, we don't see much enhancement in the pair sample. So this is all based on observations. Now let's move to simulations. So I use Illustra's TNG simulation, and then based on resolution and the size of the box, I use TNG 100. And so basically I repeat the process for the simulations to generate a sample of pairs and controls. And here is their distribution. So again, they are, well matched. So now let's look at the star formation rate. Sorry, I'm a little bit rushing, but if you have any questions, feel free to let me know. Now, one advantage of using simulations is that, we know a lot about the system, but then at the same time, when we are comparing the results of simulations with observations, we should also keep in mind that, your observations are gonna be, there will be like selection effects in observations. So you want to kind of control, you want a study that's based on simulation that's as close to observational studies as possible so that you can compare the results. So for that, so in simulations, there were actually a lot of galaxies that had unreasonably low star formation rates, even at high redshift, and which we were not going to observe in observations. So for example, here is the star formation rate distribution of all the observations of all the galaxies that were in my sample, not just pair sample, overall sample. And as you can see, there is there is some sort of cut that needs to be applied, because as you go to high redshift, you don't see this like highly low star forming galaxies. So that's what I did in my simulations. I applied this cut based on star formation rate to select my pairs and controls. And here is the result. Furthermore, in simulations, we know the 3D separation of pairs, but in observations, we only know 2D separations. So, so I also applied the effect of that. So here we have, a study based on simulations that's as close to observational study as possible. And on x-axis, we have star formation rate, projected separation, and then y-axis is star formation rate enhancement. And then I have divided them into redshift. So as you can see in the lowest redshift bin, the enhancement values are the highest. And then as you go to higher redshift, they decrease. But you still kind of see enhancements at smaller separations in all these redshift bins. And then you also see somewhat trend of this, increasing star formation rate with decreasing separation, similar to what we were seeing in the low redshift universe. But one thing is very similar to the observations, which is as you go to low redshift, as you go from low redshift to high redshift, the enhancement levels are lower. And similar thing is also seen in the AGN activity. This is AGN activity for the complete sample, but if we divide that by luminosity, now we see something very interesting. So in the high X-ray luminosity bin, this order is basically same as this order. So again, you see very high enhancement levels in the lowest redshift bin, and as you go to higher and higher redshift, the enhancement levels are lower. very interestingly, in the intermediate extraluminosity bin, not only you'd see like somewhat no enhancement up to higher separations, but maybe slight decrement. And at this moment, it's not very clear. Is it because the pairs are going from this redshift, this luminosity bin to higher luminosity bin? And that's why this number of pairs that have AGN in this luminosity bin is lower, or is it actually decreasing the extra luminosity of pairs, and that's why you don't see them? So, one way one can study this is actually tracking the paired galaxies over time, and then seeing how that luminosity change with time as they go through interaction. But again, this is very interesting that this trend is similar to what we have seen in star formation rate in observations and simulations, which is as you go to higher and higher redshift, the enhancement values are lower. And if you look at very high redshift bin of 2 to 3, you don't see almost any enhancement in the AGN activity, even in the highest X-ray luminosity bin. So, this is just basically the comparison of my simulation studies and observational studies. And of course, like I have tried to control for different selection effects and all, but there are still intrinsic differences between simulations and observations. And considering those, I would say that our results somewhat agree very well with like simulations and observations. So yeah, just to summarize, as I said, the main point is as you go from lower redshift to high redshift, the enhancement levels, so basically the boosting that you get from interaction and mergers is actually lower and lower. And at the highest redshift, we don't see any enhancements due to interactions and mergers. So that is my all my PhD work summarized in 30 minutes. Are there any quick questions? If there are long questions, we can maybe put it towards the end. If there are quick questions, I would be happy to answer.
I have a quick one.
Yeah.
Were you able to do this in your data? So bin by bolometric luminosity or X-ray luminosity?
Yeah.
IRAGN, it's a little bit tricky, but
Yeah.
bin by luminosity, and then see if you see that type of trend.
Yeah, but
So I guess you'd be dominated by the lower redshift galaxies where you have kind of middling AGN activity.
yeah. So in observations, we did try that, but we ran into low numbers. Yeah, we'll be happy to show in my paper. There is one figure. We divide by redshift and luminosity difference, and yeah, it's hard to tell. So that's what we studied, interactions and mergers. And so that is basically just, you studied the impact of a neighboring galaxy on a galaxy. And so as I expand my career and also go from the East Coast to West Coast, I continue this journey, but then I also expand from like just a neighboring galaxy to a large neighborhood of galaxy or like cities of galaxy. So basically dense environments in early galaxy cluster. So why is this important? Now, as Ben mentioned earlier in his talk on Tuesday, and as we have also seen in a lot of observations, is if you look at very dense environments in the local universe, you see very massive galaxies, but they also don't show much activity. They're kind of like red and dead. But as you go to higher and higher redshift, things look very different. So let's see how things vary at higher redshift. So again, this is the plot I have shown, and then even based on observations and simulations, we know that there are this like very dense structures growing over the cosmic time. And one thing that is happening is if you look at this high redshift part where a lot of galaxies are forming and showing a lot of activity, and as I mentioned in the low redshift case, while you do have very massive galaxies in clusters, but they are not forming stars. So exactly at what epoch they formed stars and got so massive? So there is that part, and another part is also if we look from simulations, then for example, here, if you look at around this redshift range, this intermediate redshift range, well, high redshift range, then protoclusters. So this is basically like what fraction of the cosmic star formation rate density is coming from protoclusters and their cores. So protoclusters contribute to around like even like 30% of the cosmic star formation rate. So 30% of all the star formation rate is happening in protocluster, while their volume is just like 5%. So which means that a lot of cosmic star formation rate is happening in these protoclusters. But based on local universe, we saw that clusters don't show much activity. So then how are these early protoclusters different from the local universe? And then how were they forming? What were the processes that were driving this, their very high star formation rate? So this is also seen in observations in Brand's paper, where again, if you look at like high redshift from around redshift 2 to 5, and if you look at very high milestone, then and so basically the x-axis is a measure of density. So if you go to like so from here to here, you're going to denser and denser environments. So as you look at very dense environments in early clusters when they were just forming, they are showing very high star formation rates. So clearly there is a lot of star formation happening in these dense environments, but then it's very different from local universe. So it's kind of interesting to pinpoint like around at what redshift this kind of switch is happening. And furthermore, what are the processes that are driving this high star formation rate in these dense environments, and how are the role of those processes different in the local universe versus high redshift, and so on. So there are a lot of mysteries basically. And while this does show, comparison of how dense environment can affect star formation rate of galaxies over large redshift range, we still need to pinpoint like what are the structures where this kind of nature is seen, and then are there structures where you don't see this kind of nature. So you might see actually decrement of star formation rate in dense environments similar to local universe. And then again, like if we can pinpoint exactly which structures show this kind of trend, then we can start to understand the processes that are driving this very high star formation rates. So with that motivation, as I expand from going from like neighboring galaxies to neighborhood of galaxies in very early galaxy clusters, I also expand my redshift range in my this career. So now I go from redshift 0.5 to 3, going from that to redshift of around 2 to 5. So I think I didn't emphasize enough. So all of this work is basically based on my postdoc research, which is basically done during my last 2 years. Not this work, this was done before I came here, but the work that I will show now. And so I joined UC Davis in 2021, and I'm very excited to kind of study this impact of clusters and dense environments on the star formation and aging activity to kind of complete the whole puzzle of how going from interactions to dense environments can affect the properties of galaxies across a wide redshift range. So with that, let's get started. So one thing that we really have to do is to, as I said, like if we really want to study the processes, you need to identify actual protoclusters or protostructures where this kind of trend is seen, and then you can look at different processes that are responsible for this. So to do that, what we need is actually a lot of spectroscopic observations, right? Because similar to how you need spectroscopic observations to identify if galaxies are interacting, if they are in the somewhat same redshift range, you also need information about spectroscopic redshifts to identify galaxies that are somewhat closer from each other, and then they are part of the same structure. So you need a lot of spectroscopic observations, and one of the main surveys that can help is woods. So as you can see, woods is very, very effective based on the aerial coverage and also number of spectra per degree square. So, it's very efficient and it basically gives lots and lots of spectra, as we can see in the right-hand plot. So basically it gives more than 5,000 high quality spectroscopic redshifts from redshift 2 to 6, which is again our very important epoch of galaxy evolution and assembly of structures and stuff. But along with woods, there are also other surveys that we can utilize to then identify this very massive structures in the early universe. And then we can also apply for observations. So this is kind of one of the motivation of this C3VO, which is the charting cluster construction with woods and orals. So the main motivation for this survey is to identify structures from redshift 0.5 to 5. And so orals was the initial survey, which gave a lot of structures around redshift of 1. And then for C3VO, we're kind of expanding the redshift range from lower redshift of around 1 to up to redshift of 5. And the main motivation is to identify a lot of large scale structures. And then we will go more into different motivations, but then as I mentioned, identify different processes that are driving the star formation rate and aging activity of galaxies, and along with what are the role of interaction and mergers, how does merger fraction vary in this dense environments, and how that can also impact the properties of galaxies. So a lot of goals, and let's see if we can accomplish them. So as I said, the main survey is words, but then as we will see, we can also expand it to include other surveys and then propose our own observations. So the main fields that this survey targets are Cosmos, CFHT LSD1, and ECDFS. Now these are very well-studied extragalactic fields. So they already have a lot of photometric observations as well as spectroscopic observations that we can leverage for our studies. So I kind of already went through a little bit of science questions, but yeah, the main thing is, not only we would like a sample of protostructures, but ideally we would also like sample of field or isolated galaxies so that we can compare the impact of these dense environments on galaxy properties. Similar to how in the case of interactions, we needed control sample of isolated galaxies so we can study the effect of interactions. So, and then, like how did assembly happen? How did the star formation rate and aging activity of galaxies got impacted by this dense environment? So let's see. So the first step is, of course, to identify different structures. And for that, we can use many different methods. The method we choose is called Voronoi tessellation mapping based on Monte Carlo method. So basically, this method very efficiently uses spectroscopic and photometric redshifts. And so the way it works is for each redshift slice, you select galaxies, and then you make this cells where the size of the cell is based on is related to how many points are around your neighborhood. So the higher the number density of galaxies around you, the smaller the size of the cells. And then similarly, if you have like very isolated galaxies, the sizes of the cell is going to be larger. And one of the main advantage of using this technique is also not only you can identify denser regions, but you can also identify field regions. And furthermore, it gives you a measure of density or over density at each point in your plane, right? So now, even if there is no galaxy here, if I put one galaxy here, and if I want to measure over density at this point, I already have a measure of that. So this is very, very helpful in so many different ways. And as I mentioned, we also want to identify a field. So this is helpful in that. And along with also identifying very dense regions, which then we can use to identify protostructures. So using this method, there were over 400 overdense structures were found based on C3VO observations. So out of those 400 overdense structures, the C3VO team identified 6 different structures. So, sorry, 5 different structures, and then we also targeted those structures using MOSFER and KEGG. So basically, out of those many structures, the team selected 5 very massive structures, and the goal is these structures were identified based on initial VMC maps, so the Voronoi tessellation maps, but then once you see that there is a potential structure, you can also identify members that are based on photometric redshift, and then you can target those photometric galaxies to see whether or not their SPECZ actually align with the protocluster itself. So they identified 5 different structures across these different fields, and then targeted them further using DMOS and MOS5 masks, as shown here. So on the left, we have a very massive structure in ECDFS field, and you can see the masks, outlines of the masks based on MOS5 and DMOS. And so using this, we can further identify more protocluster members in these different protoclusters. So that's all part of C3VO. And then, so we basically had many nights of MOSFER and DMOS observations. And then if we look at just C3VO observations based on MOSFER and DMOS, this is what it looks like. So as you can see, you can almost identify different structures. So this is one of the low redshift structures in the Cosmos field. So these are kind of divided by fields. So you can again see different structures in different fields. And then we also have a CDFS structure here, which is a little bit low because we are overwhelmed by redshifts in the Cosmos field. So yeah, trying to just a little bit of time. Okay, so we got few hundreds of SPECZs based on Cosmos, based on MOSFER and DMOS, about 235 from MOSFER and 234 from DMOS. And we can use all of that to identify protocluster members in the 5 structures that I mentioned before. So, but apart from these redshifts, we also have a lot of other redshifts available. So for example, in the ECDFS field, here I show spectroscopic redshifts based on Woods and MOSFER and DMOS, but then there are also a lot of other publicly available redshifts that I have shown in gray. And then if we look at the redshift distribution of coming from all these different surveys, then this is what it looks like. I also show footprint of candles and JWST based surveys JADES, but don't worry about that right now. This is like in case one would also like to use these observations, you can get idea about what kind of coverage they have with respect to other sources. So as you can see that even though we had targeted our sources using MOSFER and DMOS, we still have very decent coverage throughout the field, so that we are not extremely biased towards just our structures. And with that, so I basically as for my test study. So this is very massive, around almost 1.5 times 10 to the 15 mass protostructure. It has 6 overdense peaks. So this is basically 3D plot of this massive structure in the ECDFS field. And then the red parts are very overdense regions. So where density is more than 5 sigma, so extremely overdense regions. And even this overdense regions, all of these 6 overdense regions have mass more than 10 to the 13 solar mass. So very, very massive structure with very massive overdense peaks. And furthermore, when we had started this, the initial map that I showed for the structure. So when we had started this, there were around 20 spectroscopic members, and now that I have included C3VO observations along with a lot of publicly available observations, we have 55 spectroscopic members for this structure, and it's also very large. So it spans redshift range of 3.38 to 3.54. So very, very massive structure. And I'm very excited to see what kind of activity it shows, so which we will see in a second. So apart from this structure, I also expanded my, why is the text not showing? There should be the properties of the structure showing here. Okay, so I also expanded my redshift range from just focusing on that one massive structure to looking at other structures that are in the ECDFS field that are spanning redshift around 2.5 to 4.5. So here we have very the lowest redshift structure that is around redshift 2.67, and all of these structures have mass more than 10 to the 14.5, and then they have around 50 spectroscopic members to even 55 members for the next structure that I showed. So we have this structure around redshift 2.67, then at slightly higher redshift of around 2.8, we have this structure, and at redshift 3.3, we have third structure. We can't see the properties, and then this is the structure that I just showed that was very massive, and this is our highest redshift structure of around mass of around more than 10 to the 15 mass of more than 10 to the 15, and so very, very massive structure. All of these structures have more than 2 5 sigma peaks, and the spectroscopic members for this is around 11, but all the rest of them have 20 or more spectroscopic members. So all of these structures are very massive, very large, and very prominent and they provide excellent cases to study the impact of this dense environment on the star formation rate and aging activity of galaxies. So here is again the redshift distribution of the spectroscopic members in these different structures. And as you can see, the one that was very massive that I had initially showed, which has around 55 spectroscopic members, that stands out, and then the highest redshift structure has around 11 members. So you can kind of see that, which is understandable because it's very hard to get very high redshifts. So now that we have our structures, I should mention there are actually a lot more structures. These 6 are again kind of taken as initial cases where we can study the impact, and then we would be able to expand our sample to include other structures and also include structures in other fields. So if you look at very preliminary result for star formation rate, so this is basically, I have divided the region from redshift 3 to 4 in different environment density bins. So sigma less than 2 is basically filled, and then this is still overdense but intermediate dense environments, and then this is highly overdense environments. So these are basically peaks that I mentioned, and this is only from redshift 3 to 4, so it only includes 3 structures and not the other 3 that we still need to include. So from redshift 3 to 4, if we just focus on that, then as you can see, if we go to denser environments and at high mass, again you see higher star formation rates compared to the field galaxies, which is similar to Brian's study that I initially showed. So this is again very interesting that even though I have only included certain structures and very smaller redshift range, you still see signs of higher star formation rates in denser environments, and And then similar trend is also seen if you look at AGN activity. So if I look at X-ray or radio AGN, as you go to denser environments from left to right, you see higher AGN activity in denser environments compared to the field. So all of this again is kind of suggesting that in dense environments at this high redshift, the activity, the star formation rate and AGN activity is higher compared to the field. So as next steps, basically, first thing I will do is expand this to redshift 2 to 5, and then I'm also excited to look at like protocluster specific properties. So how does this relation look for different protoclusters and how that varies from protoclusters to protoclusters, and also with redshift. And so this will be very helpful for us to identify different processes that are driving this star formation rate in this dense environments. So yeah, so as I mentioned, I have only included these 3 structures right now. It's difficult to flip. So this 3 structures, and then I will be including this other structures. The low redshift, these are the low redshift structures, and this is the highest redshift structure at 4.14. So that we can not only identify processes that are happening for this star formation rate enhancement, but also to see if over this large redshift range, if we can identify how things vary for the low redshift cluster, relatively low redshift clusters, and also relatively high redshift clusters. So we will be able to answer a lot of questions. Another important thing that I didn't mention is if you look at a lot of protocluster and protostructure studies, they are identified based on a range of different methods. So this may include using radio sources, using very bright X-ray sources, using sub-millimeter galaxies, and all of those methods, they have their own biases and selection effects, because it is not necessary that the clusters that you select based on those kind of galaxy populations are actually representative structures, or those galaxies are representative galaxies of different clusters. So the idea is, because in this case, we have somewhat unbiased, we have selected the clusters in somewhat unbiased ways, because these are based on just spectroscopic observations. We didn't apply any criteria on the radio properties of the galaxies or X-ray properties of the galaxies. So this doesn't have similar biases. So it will be very interesting to compare if you identify protoclusters based on those methods versus our method, what did you see? And also vice versa, like if there are structures in our methods that don't show up there and structures in that method that show up here. And as I mentioned, because of our method, we are also able to identify field very properly in an unbiased way, because the spectroscopic observations are somewhat similar for clusters and field, which means that we can also compare the properties of the cluster galaxies with field galaxies in somewhat unbiased way. So the idea is to then also identify protostructures and field using this method in different other fields, and then extend this study to include larger samples. And yeah. So there are a lot of plans, but as I said, we have already identified 6 structures, and the wheels are in progress to do more. So yeah, and with that, I would like to thank you all. I would be happy to take questions. And yeah.
Any questions? Yes, please.
I have a very basic question. Sorry, I'm not super familiar with the field.
Yeah.
So in the galaxy formation plot that you showed versus redshift, why is there a turning point at redshift of around 3? And how come there's less galaxy formation as you go back in time? Yeah.
So your question is, why is this turning point? And then I think you added a little component. What was that?
Yeah, basically why that's the turning point and we're getting less galaxy formation back in time.
Yeah, so that's a great question. So it's kind of combination of multiple things. So as you go to lower and lower redshift, the gas fraction, like if you go from here to there, initially there was a lot of gas in the universe, right? So galaxies are taking a lot of gas and then forming, forming a lot of stars. So as you go to, lower and lower redshift, higher and higher redshift, as you go to early universe, the gas availability somewhat increases. But then at the same time, we also know that the more massive you get, typically, the more massive you get, the more gas you have, the more stars you're forming, right? So it's kind of combination of like, if you look at this very early galaxies, they were still forming, so they didn't have a lot of mass. So even though there is a lot of gas available, they are still kind of, doing their best forming stars, but it's not as much. So one effect is, as you go from here to there, you are getting more and more massive, but then the gas fraction is decreasing, right? So one impact is like, the increment of gas increases the star formation rate, but then the mass is kind of increasing this way, right? So yeah, I hope that answers your question.
Yeah, that.
Yeah, so it's combination of both of those things, which is resulting in very high star formation rate and aging activity around this redshift. Thank you.
Any other questions?
Yeah.
So how do you understand that you didn't see like AGN enhancement in the pair, the galaxies at high redshift? And kind of the common quenching scenarios. So there is a galaxy merger, which is a quasar, and then it blow up gas and make a quiescent galaxies. So is this any kind of conflict? What you see and this kind of common that this
Like the typical picture of like
evolution
making
of quiescent
quasar.
galaxy, yeah.
Yeah, so that's a great question. I had included that and I removed it. So that picture, so just to give context to everybody. So usually, anyway. So you basically, if you look at general picture that's shown for galaxy interactions and mergers, especially based on binary simulations, it's kind of like initially when you have first pericenter passage, you see somewhat enhancement in AGN activity and star formation rate, and then during final merger, it kind of goes into quasar phase, and then finally a lot of gas gets used, and eventually you are left with red and dead elliptical. So that picture is mainly based on very gas-rich mergers in galaxies of local universe. So if you start with a relatively lower gas fraction in galaxies, even though, so the gas fraction in them is, I think it's again like around 10% or something. So it was kind of similar to the left picture that I showed in the galaxy simulation. So if you look at, like, they still have gas, but it's not comparable to, the gas fraction in high redshift universe, right? So, so in that case, if you have like mergers in the local universe, then you can feed this gas and then trigger AGN. But then if you go to high redshift universe, though the processes that are responsible for this triggering, they themselves are weak. So the inflows that I mentioned, that fuel AGN, that inflow is very weak because the galaxy is already very disturbed at high pressure. So like it's just difficult to have strong inflows. So and that's why like the binary simulation that I showed, our results agree with that, right? So our results aren't in contrast with the studies that you mentioned, because those are mainly gas-rich mergers in the local universe.
Maybe, but people are kind of try to understand the number density of like quiescent galaxies at least 2 and the sub-millimeter galaxies at least 4, and try to make a comparison. And some people say these number densities are kind of similar, so there must be some relationships. And also Yeah, and most of the galaxies are kind of quenched at redshift 2 or even earlier. So probably, I guess these kind of scenarios are kind of aim to explain the formation of or quenching at high redshift.
I think I'm not sure about your question. So, are you saying like how the quenched galaxies form, and then if merger is the main mechanism,
Or,
and especially at high redshift?
right. But from your result, basically, the kind of pair or kind of interactions is nothing to do with
Using up all the gas and then resulting in quench. That's a good question.
One thing I'll interject is that in the simulations, high-powered AGN did seem to be enhanced. But at close separation. So, and these are the types of AGN that are traditionally invoked for quenching scenarios. So, and you do see at high redshift a high incidence of the high SFR, high volumetric luminosity AGN. So there is some, it's subtle, it seems like.
Yeah.
So it's not a complete picture of something.
Any last questions?
Yeah, can I?
Please.
I'm also wondering how to understand this kind of, you see the enhancement of AGN fraction or transformation rate in over density, but you didn't see the pair, the galaxies.
Yeah, so the very important point is for my paired galaxy, if we look at the redshift distribution, most of my galaxies have like redshift less than 2. If I can, oh here we are. So let's go. Okay. Yeah, so as you can see here, most of my galaxies have redshift less than 1.5, and then the overdense structures that I showed, and even in Brian's paper, they were from redshift 2 to 5. So that's one difference. And another thing is also, so in this case, I had actually controlled for environment. So the left-hand point here is actually, even when I look at pairs and compare the properties of isolated galaxies, I require that somewhat large-scale environment should be similar between the two, so that I can just look at, like, if you have 2 galaxies, what's the impact of that? So yeah, so it is somewhat different.
Okay.
Yeah.
Okay, well, I'll just mention that Ekta will be in Hilo for people that are in Hilo. She'll be in Hilo for the remainder of the week, either at the SMA building where we're being housed or at Gemini. So if you have any other additional questions, you can, of course, visit us at SMA or at Gemini. With that, let's thank Ekta again.